Without further ado, I want to introduce Dr. Cindy Lin from Penn State University, somebody I've known for many years now, but haven't had the chance to explicitly invite to speak. So it's a real pleasure to have you. I'm going to stop sharing and hand the screen over to you. Hopefully all will go well.
Hi everyone. Nice to be here. Thanks, Mel, for the lovely introduction, and so great to hear about electronics ecologies and the many work that you have done. Thanks, Natalie, for coordinating this, and I'm also excited to hear what both you and Sylvia will talk about in this three-part talk. I'm Cindy Lin. I'm currently an assistant professor at the College of Information Sciences and Technology at Penn State. And today I'll kind of just walk you through the chapter I've written for digital energetics, which was written with a few other folks like Anne Pasek, Zane Cooper, and Jordan Kinder, whom I could not join, unfortunately, because I was ill. So yeah, it's called Small Data on Databases and Energy Infrastructures. October 9th, 2019. I was in the office of the National Institute of Aeronautics and Space, or what some might call Indonesia's NASA, in the capital city of Indonesia, Jakarta. 3 other operators and myself were downloading satellite imagery data to send to rural and provincial offices across Indonesia. The Institute's network, however, was intermittent. It was the 3rd time we had to restart the download process. Unlike text data, satellite imagery is unstructured data and large in size. They are heavy and take time to download. A full coverage of Indonesia requires 220 satellite snapshots, or what some experts might call scenes. From remote sensor, a full satellite imagery of Indonesia can total to a minimum of 1,100 gigabytes, which is almost as large as 275 movie files. The National Institute of Aeronautics and Space, or in short form LAPAN, with whom I've introduced early on in this presentation, was legally instituted since 2016 to provide remote sensing and satellite imagery of information to provincial leaders. But that afternoon, however, leaders received no information. Instead, they sent multiple WhatsApp messages to LAPAN's operators requesting for satellite images of potential fire locations. Leaders needed to map fire locations on a high-resolution satellite imagery to seek out emergency funds from the central government authority. So 2 computer engineers from LAPAN, Raja and Camila, whom I've talked about in this chapter, believe that a more efficient process for sending satellite imagery to the rural provinces is needed, as governments worldwide turn to big tech companies to cut costs for cloud services while making data accessible at every internet-connected devices. Efficiency is influential in how data is downloaded in Indonesia today, but perhaps not in the same way that we might often think about it. Most famously associated with Frederick Winston Taylor and his systems of scientific management, Taylorism instituted the use of specialized tools, the breaking down of tasks into measurable inputs and outputs, and the introduction of managerial authority to stimulate productivity. Efficiency in Taylorism also meant the optimization of energy in relation between bodies and machines so that more work could be done. So while such optimized arrangements between bodies and machines were studied and written about in factories, startups, and platforms, my talk today explores efficiency in the design of resilient database infrastructures in Indonesia. So instead of large-scale cloud computing databases, the Indonesian engineers that I worked with during my fieldwork in LAPAN designed databases that emphasize what they call smallness. To explore how database design relates to efficiency, I focus on the design of a government-driven NoSQL, or not only structured query language database, which I use interchangeably throughout this talk with non-relational databases. This book chapter also draws from 21 months of fieldwork I've done in LAPAN, and there I work alongside Indonesian computer scientists and remote sensing scientists who are developing an online database called LAPAN Engine to stream satellite imagery and help map disaster-stricken areas on a web browser. The chapter's main arguments are the following that you see here on the slide, that databases have been historically used to maximize labor productivity are being readapted by Indonesian engineers to reverse social hierarchies in governance and reimagine a new way of building big data infrastructures. So 3 principles were being elucidated in my fieldwork with them. First being working with big data requires attending to its potential for smallness. And second, efficiency can be mobilized against management hierarchies. And last but not least, energy constraints can sometimes enrich rather than limit the autonomy of both engineers and global south nations. And in what follows in this talk, I turn briefly to how the story of efficiency in database design was initially tied to make application programmers productive in the United States, making efficiency a characteristic built into early database design and the subsequent versions. So in the 1960s to 70s, North American computer vendors, managers, and database designers, such as IBM, began to implement principles of efficiency into the design of information databases, beginning with relational models. With relational models, users wouldn't have to be specialists. A lot of this industry specialists say. They do not need to know where the information is or how computers retrieve it. They could, as in a representative of IBM, say, quote, concentrate more on their business and less on their computers. And business at worst. It was also exactly during this time that businesses began to view organizations as information processes. This started as early as the 1950s, where computers were used largely in industry spaces. Famously, Herbert Simon, an American economist and information theorist, claims that, quote, information and advice flow in all directions through the organization, end quote. Peter Drucker, an Austrian-American management theorist, also wrote in 1957 that businesses have to, quote, maintain the equilibrium between ends and means, output and effort, end quote. To do this, managers in organizations needed to handle large amounts of information. As mentioned in the 1964 article later on in Fortune that, quote, the power of the new so-called information technology is raising high management's power to make accurate decisions, end quote. Data and databases hence becomes increasingly central to the labor practices of organizations, especially for corporate attempts to centralize managerial power and inform decision-making. As databases become integral to how organizations perform information, create, and manage its labor, and as well as personal computers become ubiquitous in North America in the 1980s, database design became the site for improving programmer productivity and shaped a user base of managers. The designer of the so-called relational model, called Edgar Cott, considered in the 1982 Communications of ACM, or the Association of Computing Machinery article entitled Relational Database, a Practical Foundation for Productivity, on how information can be stored and represented in ways that will improve the application programmer's productivity and be used by end users, such as corporate advisors and managers. Call argues that relational databases can put end users in touch with information stored in computers and increase the productivity of data processing professionals in the development of applications. For instance, relational databases could allow for easy code formulation of queries and updates to be submitted from a terminal, end quote. It helped to really free programmers from irrelevant concepts that forced them to code at a low level of detail and enabled programmers to synthesize a command for processing multiple data records simultaneously and to allow end users such as managers to search databases themselves. So relational databases, in short, reduced programming time and included end users, new kinds of end users that are not just technical specialists, in the process of searching and retrieving information. Whereas the history or the North American history of relational databases was all about making informational access easier and faster for a rapidly changing user base, the development of NoSQL databases was the product of a different imperative, the need to constant uptime for a consumer user base. Avinash Lachma, the developer of an early NoSQL database, said in an interview, quote, "At Amazon, we had to build Dynamo, the first NoSQL database, to be multi-sided, so it could survive a data center outage without causing downtime to Amazon.com, where downtime was directly correlated to losses of millions of dollars. So building resilient services is a higher priority than performance in today's always-on connected world. I'm more likely to abandon a site or stop using a service if it incurs frequent outages than if it's a fraction of a second slower, end quote. In this quote, Lachman prioritized a database ability to maintain a resilient infrastructure over the speed of information retrieval, moving away from inefficient time wasting to fearing the loss of users. A different model of value creation was designed into NoSQL databases. It's this illusion of the always-on connected world across sites that Lachman hopes to maintain for the tech world. The desire to build resilient NoSQL database infrastructures in North America, however, brings up an interesting question for Indonesia. What is continuous flow of data and revenue in a place where intermittent connection and energy is common? In the next section, I focus on developing how Lapan's engineers in Indonesia think of efficiency, especially when databases are required to send information for disaster and emergency mapping and planning to rural officials. It started with what I thought was an innocent question about data. How do you store it? To store satellite imagery into a database, Raja and Camila, my two key interlocutors, replied me one afternoon at October 2019, quote, "You have to reformat it." Raja and Camila are two Indonesian computer scientists who have come to enjoy afternoon conversations with, drawing images of how data can be restructured, such as what you see here on the screen, on whiteboards throughout the offices that we were inhabiting. Both of them are key builders of Lapan Engine, a high-performance computer storage, they call it that uses NoSQL databases to store and stream satellite imagery for public use. Camila claimed that satellite imagery is the most difficult data to store. I asked why, curious as to what can make an image so difficult to keep. He simply replied, "No, silly. Satellite images just contain too much information. Each pixel of satellite imagery can provide basic data, from brightness and the height of mountains to complex process information, such as atmospheric quality, water pollution, and the presence of fires. Hence, to make it easy to sort and search, they needed to introduce structure to such data. And one of the first structures I was introduced to was through the alteration of the database architecture itself. Typically, databases such as relational databases are built with a master-slave architecture. This architecture meant that the master node receives and stores all the information, which will then be transmitted to slave nodes for it to be read. However, if the master node breaks down due to faulty hardware or failure in network, for instance, a database will stop working. In the case of Lapan Engine, this would mean that it will stop streaming satellite imagery to provincial leaders in rural Indonesia. Raja and Camila wanted to really move away from this central reliance on one database server or the master node, which is typically located in Jakarta, the capital city of Indonesia. Raja explained to me why, quote, "that this database reminds me of how we are treated as lower-level government workers. We have no ability to choose what we can do and how to do it. This makes us unable to provide information to everyone, even if the leaders of our country promise to do so. It also makes it difficult for rural district and village officials who would like to access this data readily, but instead wait for operators to finish downloading such data or make a personal trip to Jakarta itself in order to store it in their own hard disk." End quote. Raja chose to work with Apache Cassandra, the free open source NoSQL database that account introduced early on in this presentation. It's a database with a network that has no master nodes. The same data in a row can be replicated across several nodes, and all nodes can now store data. This masterless ring design meant that if one node was broken, the other nodes will continue operating. Cassandra mitigated the risk of data loss and access to information during regular electricity outages and network connections that Indonesians experience. The replication of data across different nodes also allow Raja and Camila to reimagine how data should be distributed without complete reliance on a single node. Nodes are now spread across different data centers, ensuring that if an entire data center somehow fails in rural Indonesia, a replica of the same row of data will be available in Jakarta. Thus, database design in Lapan is built with an aspiration to really transform bureaucratic hierarchy. Creators felt a new social world is made possible with the properties of databases, one without masters and slaves. This master-slave metaphor as such had actual material effects and ensured that information storage and retrieval was not only centralized in Jakarta, but possible to access from rural Indonesia. It also served as a direct intervention against the growing centralization of information that has been the ongoing concern for various government researchers in Indonesia itself. Now, let me elaborate on how data can be prepared to reduce the need for stable electricity and high bandwidth. For Lapan engine, Raja and Camila imposed a grid on the satellite scene. As pictured here, the shaded white area refers to the tiles of the satellite scene, designated with a series of values. These values included the location of where each tile can be found in the whole satellite scene, and the date and time each tile was photographed. In the grid, each small chip becomes a satellite tile, and the large satellite imagery is now smaller and easier to search and retrieve over limited bandwidth and electricity flow. This data transformation was necessary if Lapan wanted non-programmer end users living in rural provinces to download small batches of data instead of a large whole satellite imagery filled with irrelevant places that they do not need to have mapped. Designing for such unique resource constraints were particular to Indonesian researchers like Raja and Camila. Camila added that they're not met by, quote, rich researchers who can compute as much as they want, end quote. And I think we can all empathize with this point, made quite a bit, right? Now being in a College of Information Sciences and Technology, there are certain constraints that researchers outside of large universities or large companies would face, right? And therefore the move towards free cloud services. But for people like Raja and Camila, they couldn't really contract out services from large tech companies, so they really had to rebuild this infrastructure from scratch. So here, the tiling of images ensures quick retrieval for users to gain access to data with as little electricity and bandwidth. In sum, I show how Raja and Camila from Lapan sought out this very different kind of data infrastructure by developing a storage design that attended to resiliency and energy constraints. By insisting on the particularity of satellite imagery and the ways such data can be stored and retrieved in a place of constant breakdown, Raja and Camila showed how information access can be decentralized. Lapan engine is an attempt at challenging the sole authority of central government authorities over satellite imagery by ensuring that rural, district, and village leaders can better obtain data with such constraints. Knowing that building such a database is possible only reassured Raja and Camila, who could not rely on the cloud computing infrastructures of companies such as Google or Amazon. It retained the independence of its agency itself and challenged the ubiquity of public-private partnerships that now fund and also build public sector data infrastructures elsewhere. For instance, in the US from 2007 to 2019, the Department of Homeland Security contracts and subcontracts services from firms such as Amazon and Microsoft the most. And there's an urgent need for public and I would say even community-owned big data infrastructures. And Lapan engine actually showed me empirically how to build one. So in addition, Raja and Camila have designed a database that questions the historical determinacy of databases as necessary tools for increasing programmer productivity and enacting managerial hierarchy as they once were designed for in North America. They show how efficiency did not necessarily mean the conversion of energy inputs such as electricity and labor into fast and rapid delivery of information. Efficiency, in other words, is interpreted and implemented variedly in different energy cultures. In Indonesia, it's about creating a resilient infrastructure for leaders to govern and manage disasters within their own purviews, rather than ensuring that no downtime can be occurred when we are trying to shop on Amazon Marketplace, for instance. It follows then that producing small data from the global south is more than simply thrifting on electricity or improving the productivity of operators. And I might even argue here that, there's a lot to be learned from places where, the planet's future has already been mapped, right? In a country like Indonesia, where there's massive palm oil plantations and huge peatland fires occurring every year, we might actually consider some of this improvisation and innovation around big data as necessary solutions that, might be possible elsewhere as well. So it must also include understanding how relations of power can be inscribed into database design and who as a result has access to information within seemingly immaterial, non-hierarchical, and potentially green data relations. All right, thank you so much for listening.